So hi and welcome to today's webinar. My name is Matthew McKnight. I'm a technical specialist working for Autodesk out of the Melbourne office. The topic today is increase your innovation capacity with Autodesk Shape Generator. Let's jump straight into it. So I want to start our webinar today by talking to you about a facility that's located in San Francisco. This is called P9. And P9 is sort of like a dream space for engineers and designers. It's inside the confines of this space is all these wonderful, machines that most engineers and designers can only ever dream of having access to. And these, machines in this workspace is used to help develop the solutions that our programmers and that work on. But they are also used by what are called artists in residence. And these artists in residence come and they do a residence at P9 where they really push our solutions to the limit. A really good example of this is shown in the following video. And this video highlights to you the use of some generative design technology. And this technology really is showing you, some of the future of where generative design or design will be in the future. In this instance, the artist has come up with the idea of creating the structural section of an archer's bow, and they're going to use this technology to design the product for them. So, in essence, the machine or the software is creating the geometry based on parameters, the loads, the volume of space that the material can occupy, the material that the part is being made out of, and then it comes up with that optimized shape. You can see here that the part is actually being milled out of a solid block of aluminium. Could have quite easily have been 3D printed out of aluminium or titanium, say for instance, and then it's assembled to show that the bow is a functional piece of geometry, not necessarily just a piece of art. I suppose I like this video because it really does highlight the changing landscapes of manufacturers and the new innovative ways that manufacturers in the future will use technology to help improve their designs, but also to segregate themselves away from their competitors. And this really does bode well in the future of making things. We've talked, if you've attended any of my webinars or seminars of recent, you will have seen or heard me talk about the future of making things. In particular, we talk about three disruptive factors: the methods of production, the demand of consumers, and the types of products that we make. And each of these has elements of generative design contained within inside them. So new manufacturing processes and the new ways that we design our products is specifically related to generative design. The demand from the customer is, there's a drive now for more optimized solutions and products. And the products themselves, they need to be lighter, they need to be smarter, they need to be better designed. So if you look at each of these disruptive factors, there are elements contained inside of each of those that are particular to the need to start considering the ways that generative design can help you in your design processes. If we look at the product innovation platform, and we've talked about this previously, I want to highlight to you the fact that inside the design section of the product innovation platform, you can see there that generative design plays a large role in the future vision of our technology. And then if we move forward and then look at, well, why would you use simulation? We've had this discussion, a number of times over the last 6 or 12 months in a number of webinars that I've run, is that simulation really does help make better decisions, but more importantly, it helps you make those decisions sooner. And we'll try and highlight that through today's webinar. But if you look at some of the questions that engineers are asking themselves day in, day out, will my part fail? Will it overheat? How can I make it, produce components faster? How strong does it need to be? Will failure occur? And if so, when? So all of these types of questions engineers are asking themselves. They're trying to predict the answers to these, and that's where simulation plays a role. And if we look at a graph highlighting to us our use of simulation, it's actually, when we use simulation, it's probably around the design engineering, maybe the testing stage of the life cycle of a product. The problem with doing it later is that the cost associated with change is much higher. And if we've gone through all of the stages of producing a detailed design, the tooling, maybe even made some parts, then the cost associated with making change that late in the life cycle is quite possibly prohibitive and could potentially put a project at risk. If you consider pushing that forward or much earlier in the design stage, then the cost associated with making the change is significantly less because the change itself is much easier. And generative design really does push the boundary because it's pushing a lot of that simulation and design stage right back to the conceptual, very early stage design in the life cycle. If we consider the advantages of using simulation, there's obviously time. If we can reduce the number of iterations that we need to make of our parts, then it's going to save us time. Potentially it's going to save us money as a consequence of that, not only the development time, but also the cost to actually develop prototypes and test your products. Maybe even more importantly, it's going to give us some insight into the way that our products are going to perform. But I'd like to highlight today to you the way that simulation in particular, how some of this predictive analysis or generative design can help you innovate new products. So a couple of quick examples. So some of you may have seen this example before. I've used it a couple of times before, but I think it's quite innovative in the sense that this product for this customer could completely radicalize or change and disrupt the industry that it's in. It's a heat exchanger. It's a product that was designed using generative design. So it wasn't designed necessarily by a human. The human put in the parameters associated with the volume, the size, the space that could be used in this case, the material, maybe the material that was being cooled or heated, and then the software took over and created the geometry of the part. So, if you consider this for a moment, that it's a very complex part, it would have taken considerable effort for a human to have designed this. But not only that, but then if you consider the way that it would be manufactured, it would have been extremely difficult to manufacture this part. It would have been difficult to cast it or fabricate it, machine it, whatever you want to use, extremely difficult. So much so that really the only way that you could manufacture this part is by using additive manufacturing or 3D printing, which is what's the case in this component here. So if you consider maybe 10, 15 years ago, this type of product wasn't possible. But now with the technologies that are coming of age, there are now the opportunities for customers or manufacturers to completely radicalize and disrupt their industries by offering these types of products. Here's another example. This is a product that was developed by Under Armour. It was a shoe that they've recently announced and released. And you can see here that the sole of which, or the midsole of the shoe, has actually been designed using generative design. Again, using some of our technology to do so. In this instance, it's one of the first, I think the first 3D printed shoe to have been released on the market as a commercial product. And again, another avenue where manufacturers are using generative design in combination with other manufacturing techniques to create components that are completely disrupting the traditional ways that we would manufacture things. So what is generative design then? Well, I like to look at generative design by firstly looking back at what a traditional analysis is. And traditional analysis, as I see it, is a very iterative process. We start out with a volume, a space, and then we run an analysis on it. We look at the results of our analysis. We remove some material, try and optimize it a bit. We run another analysis. We remove some more material, and if we haven't given up by this stage, we might run another analysis, make some changes, run another analysis, make some changes, and then confirm that our part meets our desired needs. The problem here is that we're really, we're limited on our ability to be able to take from the feedback that we're getting from our analysis and then apply that to the geometry. And this is where predictive analysis or generative design really turns that process on its head. We start with the same block of material or space, We apply the same loads and constraints. And then the predictive analysis comes back and then suggests to us topology or a shape that is optimized for that specific loading criteria. We can then replicate that with inside of our CAD geometry. And then, as a final step, just confirm that the structural load can be supported by the shape that was generated, recognizing that the shape that was generated in this instance was generated not based on the load itself, but the load path through the part, and our desire to remove material. So this is where Shape Generator comes into it. Shape Generator came about in the 2016 release of Inventor, and includes the ability to be able to use this predictive generative design type of analysis. So I'm going to give you a really quick introduction to how you can use Shape Generator, and then we'll look at a couple of examples of ways that it can be used. So bear with me as I quickly switch. So here we are inside of Inventor. I've got a very simple part, and this is highlights the fact that you don't need to be designing complex parts. Maybe you're just looking to minimize the weight of your components to try and minimize the overall package or design of a product, and that gives your customer a performance enhancement. Maybe it means that they can carry more load if they're a trailer manufacturer and they're trying to reduce weight of their trailer. The fact that they can retain the same strength or sufficient strength to carry more load could be a critical difference between you and your competitors. So in this example, that's exactly what we're going to do, is we're going to look and see if we can make some changes to our design, reduce the load, reduce the weight of our part, but still allow us to carry the load that we require of the part. So you'll see here inside of the menu structure, we've got the Shape Generator icon located here. Now we can access that by going to our environments and stress analysis. It's going to enter us into the same environment. In the first instance, I've already got a Shape Generator study set up, but what I'll do in this instance is actually create a new study here by going create new study. You'll see here we're given the typical analysis types that we've come to expect with inside of Inventor simulation, and that is a static analysis and modal analysis. Now what I want to highlight to you is this one at the bottom here, Shape Generator. So this is where we get the generative design aspects directly inside of Inventor Professional. If I click OK, it's going to give us a little pop-up box, tells us a little bit about our design. Highlights to you that you should perform a separate analysis to verify the stress levels are acceptable. And I will just highlight that again to you. So it's carried over any materials that we've assigned to the parts. And notice that on our toolbar, that the first section of our toolbar is reasonably generic. If we're accustomed to using Inventor simulation, then you would feel comfortable inside of this environment already. So in this case, we can add a couple of fixed loads, and I'll just fix those bottom faces down the bottom there. We can also add fixed constraints. We can also add pinned or frictionless constraints. Let's add a force, and I'll just apply that to a face over here. And I'm going to give it an arbitrary number of 1,000 newtons, and you could just as easily apply pressure, bearing, moment, or gravity to the part as well. Now this is where it gets really interesting, is because once I move past our loads and constraints and materials, we then get some tools that enable us to specify how we want our Shape Generator study to run. In the first instance, we've got the ability to be able to preserve regions. This is where we want to retain specific geometry of our part without the Shape Generator removing that geometry. You'll note that if I click on some geometry, I'm then given a box that I can then drag over specific areas of my model or my design that will then ensure that that geometry is retained. It's not removed from the analysis. So I can do that. I can do it on both, in this case, a box shape, or it could be a cylindrical shape as well. We'll hit OK. You can see here that it's just highlighted. Likewise, I can also access a symmetrical plane through the part. So if I want to make sure that the part is symmetrical, then I can do that as well. So I'm going to turn on or off any symmetry that I want associated with the part. In this case, what I want to do is I want to make sure that the part is symmetrical about the left and the right, so I've chosen the plane associated with that. In this instance, then we can hit OK. If I go inside of the shape generator settings, you'll see that this is where the real specifications come down to how we're going to run the analysis. So in the first instance, we can see our original mass of our part. We're given a mass target. How do we want to remove material, and what's our goal associated with this? In this case, we want to remove it by either a percentage or as a target mass. So I could reduce, or increase the number, and you can see the associated number inside the target mass is going up or down. But I could also just go in here and type the value, and it will give us the reduction in that case. We can also put in a minimum member section, member size. So if the shape generator study comes back with all kinds of webbing in the part, if we want to make sure that we've got a minimum section, then we can come in here and maybe put that our minimum is 5 millimeters. Beyond that, we can adjust our mesh resolution, so make it coarse or fine, hit OK, and you will see that in the instance where you've got quite a small minimum member size, quite a large mesh, we'll actually come back to you and warn you associated with that. The idea here is that you would then go back and modify this, and you can see here that it's recommending that I try a mesh resolution size of 0.2, or inversely I go over here and then adjust that. You can see that as I adjust between those two, it's going to adjust the number that I need in the associated dialog box. Beyond that, really all I do is hit generate shape. Now I'm not going to do that because it will take a few minutes for it to solve. Instead, let's go back and look at a study that I've already run. So here's the same part, and I'll hit activate, and you'll see that here's the results that have come back. You can see here that the goals and the setup was slightly different to what I've run just a few moments ago. But you will note that the part does come back, and it gives us some insight about the loading through the part. Now remember that this loading is really talking about the load path. It's not specific to the number associated with the load. So you will need to confirm as a secondary operation that the part can support that load. But you will see here that the geometry does give us a really good indication of those areas of our design that if we wanted to remove material, potentially those areas of the design that may not be adding to the overall strength of the part. So you can see here that I've got some areas or pockets. Maybe I'll rotate around so that I'm looking at the front of the part. You can see that I could potentially pocket out the part on the left and the right. I could potentially pocket out the bottom here. And you'll note down towards the bottom brackets where the part mounts onto the part, I could potentially even remove some of the material in this localized area as well. So that gives us some really nice insight into the part and the ways that we can optimize it. How do we do that? Well, we do that by promoting the shape. If I click on Promote Shape, you'll see that I can either promote the shape to the current part file, which gives me the ability to be able to use that then in the means of being able to then use it as a template to create the geometry. Or I can create an STL file, in which case it wouldn't export the STL file. Maybe I want to 3D print that optimized shape directly to a 3D printer. So in this case, I'll use to the current part, and you'll see here that the part has been promoted, and I can see the geometry through the part, which gives me the ability, like I said, to go on, create sketches that define the shape of the material that we want to remove, and then functionally remove that from the part. It creates shape generator studies, creates some really interesting geometry. If I go and have a look at this part here, so here was a different part, and I applied a different load. This was a torsional load on this end face here, with a fixed constraint on this end face here. And you'll note that if I activate the study, you'll see a nice lattice type structure, which is almost what you would expect to try and support the type of load that's happening. Now in this case I created symmetry about two planes to ensure that I was getting some sort of symmetrical geometry that I could use, and you can see here that now potentially I could export that geometry and start using that as a means to create this optimized part. Remember, again, as a secondary process, after you've used the shape to then remove material from your part, and you'll need to run another analysis to confirm that the part can support the loads based on the constraints and setup of the geometry. Okay, so let's go back to our presentation. So let's have a quick look at another couple of examples of how using shape generator can help you increase your innovation capacity. So here's two relatively quick examples. Again, using reasonably generic geometry to highlight the fact that this can be used across a wide range of industries. So here we have a design. It's a hydraulic or pneumatic cylinder. It's a clamping component that's holding down some sheet metal, and it's part of a larger assembly. And the idea here would be to optimize our design. Maybe we're looking at changing the hydraulic or pneumatic cylinder to run a higher performance, to run the machine at a higher speed, which can maybe give us a competitive advantage in our market. Now what we can do is, in this instance, we're using force effect, available from your web browser or directly inside of Inventor to understand the loads of our part, and then given those loads we can run a shape generator study directly inside Inventor to then get this optimized shape of our design. You can see after we've then migrated that geometry inside of Inventor, we can quickly replicate the form of our part and understand it. And then in this instance what we've done is we've run further analysis using Nastran InCAD to understand the part and its susceptibility to a different failure criteria. We're actually even considering different materials, which is one of the key aspects of being able to run an analysis like this is the ability to be able to quickly assess whether various different shapes, geometry, materials, how they're going to affect our design. You can see in this case by using a different material, I believe a plastic, means that the part would potentially fail due to buckling. So again, the value of using shape generator in here gives us the ability to be able to quickly and easily generate an optimized shape, test that part, make sure it's going to structurally meet our requirements, and then improve the product performance of our design. Likewise in this case as well, where we have another example, we've got maybe a casting or a machined component, and we want to look at a design alternative. In this instance we're using Fault, our data management system, to replicate an existing design and then to quickly run an analysis using the shape generator study. Like we showed before, it's very quick and easy to set up one of these studies. We use some of the typical setup features that we would use if we're accustomed to using Inventor simulation, the constraints and loads. We apply some information associated with how much material we want to remove, and then we quickly and easily can run the analysis. We're promoting that shape and then replicating the geometry within. So you can see here a couple of really interesting examples of the use of shape generator on some reasonably practical examples of our parts inside of Inventor. So let me have a quick look and see whether there are any questions from anyone during the session. No questions today. So with that, let me just close out today's session by giving you my contact details. If anyone has any questions that they would like to ask, feel free to come back to me after the session. My details are there. If you would like further information about Inventor or shape generator or generative design, also feel free to contact any of our resellers. You can find details of them on the Autodesk website at autodesk.com/resellers. And you'll also find more information about Inventor and shape generator on the autodesk.com website. Otherwise, I'll thank you for your time today. Let you get out and enjoy this cold, miserable winter's day in Melbourne. But hopefully we'll see you in a week or so's time at the next webinar. Thanks for joining me today. Bye for now.